we're going to talk a little bit about the quantum mechanic model. I'll give you a little bit of history. I used to give you all the guys that, you know, this guy did this and this guy's responsible for this. And then I always got the same question, do we have to know that? And then I'd say, well, no. And they'd be like, well, you just killed the tree for that. So I kind of cut that out, and I'll just give you kind of the Coles Note version. And even this will just kind of explain to you what the most current explanation of what an atom actually looks like. That's where we're going to start today, what atoms actually look like. So you do have some stuff to copy down here, so I'll let you do that real quick here, and then we'll talk about the quantum mechanic model here and other stuff we'll do with that. So quantum mechanic model. This is what we believe today an atom looks like. Most current explanation includes an electron cloud. The electrons have certain energy levels, but the exact location cannot be defined. The lower energies have a greater probability of holding electrons, and higher energy levels. The number of protons in the nucleus is defined as the atomic number. We'll talk about that in a little bit here. The number of electrons in neutral atoms is equal to the number of protons. So electrons and protons are equal if it's neutral. And we're going to skip that one for right now. The most stable state of an atom is called its ground state, when all the electrons are in the lowest energy possible. And we will draw some diagrams on that next week, so you're just going to have to be patient. Okay, don't freak out yet. You can do that next week, all right? And lastly, a definition, a term we'll always use, so make sure you know this one. Electrons in the energy level furthest away from the nucleus, okay, and we'll draw some diagrams again. I'll show you that to you. Valence electrons are what they called, okay, valence. So, now, you might have seen lots of diagrams. I don't know which ones you guys are familiar with. Like I said, we're going to use a particular one in here called the Bohr diagram. Have you guys ever used Bohr diagrams before? Yeah? Few of you, okay. We will use Bohr diagrams here eventually. Bohr diagrams are good for us. They're easy to draw. But is that really what happens? And the answer is not quite, no. But it's the best thing that we have probably for showing where electrons are, et cetera, et cetera. There's other guys along the way. So some guy came up with, for example, the neutron, right? He was the first guy to discover neutrons. There was, you know, the talk about where the electrons were located. Where does the neutrons located? So there was different theories along the way. Each guy had their own little thing. There's guys like Chadwick, Niels Bohr, okay? Rutherford was another contributor to this, and so on and so on, okay? Now, you don't have to know this because we're going to do this, but a Bohr diagram kind of looks like this here. And for those of you guys who remember, I don't know, protons and neutrons went in the nucleus here. That was his theory. That's correct, and there's nothing wrong with that. Protons and neutrons make up the nucleus. And then electrons would orbit around here, okay? How many electrons, do you remember how many electrons can you put in the first energy level? 2, yeah. So you can put 2 in here, okay? How many go in the next one? How many could you have in the next one? Yeah, it is 8. How many in the next one after that? Somebody else. Anyone else? How many electrons could you put in there? And if you're like, what's he talking about right now? I have no idea. What's an electron? Well, that's okay. We'll get there, okay? Yeah. Yeah, there's another 8 in there. How much is the next one? That's the trick question. We'll figure out how much you actually know here. Yeah. No. Nope. Well, no. It's more than 8. Technically, 18 is the right answer. There is different, we'll talk about that when we get there, so there's a little bit of variation on that, so, but we're not going to go that far, okay? That's a Bohr diagram, and we'll talk about those later. So just be patient, all right? So if you didn't know what I just did there, it's okay. Okay, we're going to do something really a lot simpler today. But that's a Bohr diagram. It's nice and neat. It's easy to put electrons there. It's nice to know where everything is. It's great. But that's not really what an atom looks like. An atom would look something more like this here, for example. And this is this quantum mechanic model. So you got your protons and neutrons there. Where are the electrons located? They're in a cloud. So you can't tell me that, for example, you know, if you looked at an atom, you can't say, oh, that electron's got to be on this ring right there, and the other one's like right here kind of thing. You can't tell me that, okay? They go in an elliptical orbit, so sometimes they're a little bit closer to the nucleus, and sometimes they're a little bit farther away. Okay. Is there going to be 2 electrons that are really close to the nucleus? Yes, there will be. Is there going to be some that are a little bit farther away? Yes, there are. Where are they exactly? Tough to say. Okay, so I don't know how to draw that cloud because I can't draw. You'll figure that out pretty soon. Wait till we get to the hammer. Like when I have to draw the hammer, it's interesting. Okay, but they're in a cloud, so they can be kind of, I know it looks like a flower, I get that. That's a cloud, okay? They can be anywhere in here kind of thing, all the way around. So they might be a little bit closer, and they might go around that orbit, and they might be a little bit farther away, okay? Like I said, this, hard to draw, you know. What are you gonna do, draw that for all of them? This is easier for us. Okay, so that's why we use board diagrams to help us. But that's kind of more accurate. Sometimes they're closer, sometimes they're farther away. Okay, they're not exactly on a ring, so you can't say, oh, they're right here all the time. All right, so that's the quantum mechanic model. And we're going to talk about how the number of protons is the same as the atomic number, and the number of electrons and protons have to equal out. I have a present for you guys today, because you came for the second day and you put up with me for the first one. I like presents. It's chocolate. Who doesn't like chocolate? Good, I don't either. It's not chocolate. I'm lying. I would never give you chocolate in class. That's silly. I have periodic tables for you guys. That's more my style. All right? So, let's do that. All right, because this is funny. Whatever you do, don't fold them. I'm just kidding. You can do whatever you want with them. They're yours. It's always funny. I get to, everyone panics, say, it's funny. I always wait for you guys to fold them, and then I say that. It's fun. It's a little bit funny, okay? You can do whatever you want. You can fold them again if you want. Make it into a quarter, put it in your back pocket. When you're out and about, you can just pull it out and say, hey, a periodic table. So this is the one we're going to use. Who used this one last year? You guys remember? Should be the same roughly, I hope. Roughly, give or take a bit. These are brand new. I just made them for you last night. So there's your periodic tables. Lots of the elements there. Polyatomic ions in the top left. We'll do a lot of that stuff here coming up Monday, Tuesday kind of thing. So stick around. It'll be fun. Backside, you have on the backside. Solubility chart, we'll use that extensively this year. I don't know how much you used it last year or not, but we'll use that a lot. I don't know if you did or not to even have that. Some basic unit conversions, I guess. There's nothing too fancy there. Hopefully we're able to do those and whatever. Flame color of elements. That's fine too. Sometimes I used to put the flame color of ions there. We'll do that in the lab and see if I can't set the lab bench on fire again. And if that happens, don't panic too much. I will. But that's always fun. We'll do that in Unit 3. How's that? Okay. On the right side, you get all the Chem 20 formulas that you'll need for the entire year. How's that? See, I'm a nice guy. Hey, we want you to do well, yes? Every formula that you're going to need is right there for you. And they might not make a lot of sense for you right now, but they're there, okay? And you'll use them by the end of the year. So all that stuff is there for you. I can tell you this, you'll get one of these. Oh, by the way, sorry, you can color your periodic table. I'll tell you where I got that from. There's no surprise. This is the grade 12 data booklet that you're going to get next year. So we'll give you one of these. It's got a bunch of stuff in here. And if you open it up, that is your periodic table. Yours is not in color because our color printer is always like missing orange or yellow. And then stuff just doesn't come out properly. So I don't make you color ones, but if you want this, you can go just type in on the website, data booklet, Chem 30, Alberta. It'll pop up. Make sure it's this one though, the orange one, 2010, because that's the most recent one. And this will pop up. You can print it off at home and make your own if you want. It's up to you. It's fun. Okay? But that's exactly what you get. This is the one you're going to have next year. And that other stuff that I got for you there is also in here. What you will not find in here is any formulas, because next year you do not get any formulas. Okay? So grade 11 you do, 12 no. Okay? So no formulas in here, but there's a bunch of other stuff. Okay, so that's where that comes from. And like I said, if you want your own, you want to color coordinate, you can do that. You can write little notes on your periodic. These are yours for you to have. If you lose them, try not to, please. But if you lose one, I have extras here. I'm going to put them up on top of the filing cabinet. Just come grab one. You don't have to ask me. You don't have to say, hey, I missed, I lost it, whatever. Just grab one. Okay. Just try not to grab one every day, please. But they're always here for you. You can write, make cheat notes, whatever you want. Tomorrow, maybe, probably not today. Probably tomorrow we're going to talk about what Group 1's called the alkali metals. Group 2 is the alkaline earth metals. 3 to 12 are transition. If you want to write that on your periodic table, I don't care. You want to write down some charges here and there, go ahead. You can do whatever you want with this. The only thing is you do not get to use yours for quizzes and tests. So when I give you a quiz or a test, or midterm or final exam, I'll give you, first of all, what you see right now, basically, a blank periodic table, whatever you see now, and a quiz or a test, basically, and you'll use that. Okay, so you won't be allowed to use your own, so just kind of keep that in mind. Okay? Good? Questions, anyone? Merry Christmas, early. Happy second day of school. Present. Okay, today we're going to talk about atomic numbers and masses. So we're going to go back to the proton-neutron thing, and we're going to talk about protons, electrons, neutrons, I guess I should say. We're going to talk about that stuff today. So on your periodic table, here's what we're going to do. We're going to find argon. Some of you guys might say, argon where? I'll tell you, it's on the far right. That's where it went. Seriously. Come on, it's not that bad, eh? Argon, where? It's on the far right there, third one down. So go ahead and find that, argon. Atomic number. What's the atomic number? Atomic number, of course, is the one on the left side of the periodic table. It's the one that tells you where it's located on this chart here. And it is number, of course, what, 18? Okay, so we're going to put an 18 in there. That's the atomic number. Tells you where it is located. Obviously 1 through 100 and some there. The mass number, okay? The mass number, the atomic mass number, is the number on the right-hand side. It tells you how much this atom would weigh. So the mass number, of course, is, it says there, 39.95. And I'll write that down, but don't write that down. So it's 39.95. And what I'm going to get you guys to do is round that up or down accordingly. So in this case here, we're going to round it to the nearest whole number. In this case, we'll round that 39.95 up to 40. Okay, so we're going to put a 40 in here. Remember, the atomic number from the notes on the last slide says the atomic number and the number of protons are the same, right? So this tells you how many protons are in the nucleus. That's what the first number tells you. So we're going to have 18 protons. And for protons, we're going to use a little symbol to denote that. Instead of writing protons all the time, we're going to put a P with a positive sign up there. Okay? P with a positive sign. That's how we're going to denote all protons. Protons are positively charged, what we call subatomic particles. So they're of the atom. They're tinier pieces of the atom. Okay? In electrically neutral, or in neutral atoms, if we have 18 positives, how many negatives do we have to have out to cancel them out? It's not a trick question. 18. Yeah, 18. Okay. So if you're not sure, get a calculator. All right. So seriously, you guys. Number of electrons. E with a little minus sign because they're negative. Okay. Okay, now when we look at a proton, when we look at the atom here, I drew 2 of them here. We both know, however you wish to draw this, all the mass of an atom comes from its nucleus. And when I say that, I'm lying a little bit, but basically that's where it comes from. So if you look at here, that's the mass of the atom. How much does an electron weigh? It weighs almost nothing. Okay, same thing here. All the weight comes from right here, okay? So if you want to use that diagram, the quantum mechanic model. All the weight comes from the nucleus part. So I can tell you this, we pretend, and this is not true, you'll find out pretty quickly that I'm going to lie to you for probably a lot of this class, because when you get to university they'll be like, oh, you're so naive, eh? And then they'll fix everything that I tell you. But it's true, but it's kind of got little things here and there. So it's true, I'm not just making stuff up, but there is other little details, right? When we talk about nucleus and where the weight comes from, we assume that the protons and neutrons weigh about the same. And that's not quite true, but we're going to assume that for right now. So if my weight of 40 here, this is my weight here, okay? This atom weighs 40 and 18 of those are protons, the rest have to be neutrons, all right? So in this particular case here, well, if the weight's 40, we've got 18 protons, we need another what? 22? We need another 22 neutrons to make up that weight of 40, right? If you got 18 and they each weigh 1, and we're assuming that the neutron weighs the same, okay? We need another 22 of those to make that weight to 40, all right? So the protons and the neutrons, and if you want to write any of this down, that's great. If protons and neutrons have to give you the mass of that atom, okay? Always. So in this particular case, we have 22 neutrons. Neutrons are represented by N for neutron. Neutrons don't have a charge, right? We already used positive and negative, so we put a little 0 up there, basically nothing, okay? Sometimes I like to refer to the neutrons as jimmies.
What? Oh.
Yeah. Some people aren't Jimmy Neutron. Well, I'll just say it again. There we go. Okay, Jimmy Neutron. So I call them jimmies. I got the jimmies. All right. So that's neutrons there. Okay, good. Atom representation, I hate to kind of say this because I just put it on there, but you know, honestly, I don't really care about this. I never ask you this, but if you're talking about atom representation, argon, you know, you can write it like this, for example, 18 and 40, so the atomic number, the atomic mass. If you want to have 18 and 39.95, you got to be one of those people that have to be right down to the decimal. Fine, don't care. Okay. You may also see this sometimes, 40 with an argon. So you might just see the mass there, and there's a reason for that, and I'll explain that in a little bit here. Sometimes you will see 40, and down here you'll see the 18 here. So those are all different ways you can represent the atom, whatever, okay, or just look on your periodic table. All right. Let's find some strontium here. Let's find this one. Number 38. Let's find that somewhere. I wonder what it could be. Oops. So 38, you're going to look in the second column there, I guess. And oh, look, it's strontium. How about that? So we'll put an SR there and the strontium. Okay. Now, we already gave you the numbers here, so you know you might have to fill in some different parts here. If the atomic number is 38, how many protons does it have? Oh, no, not you. Somebody else. 38. And if it's got 38 positives, protons, how many electrons do we need? Sure. Nope. How many electrons? Yep, perfect. And then, okay, if I have a weight of 88, so obviously it's pretty heavy here, you could call it a heavy metal. Anyway, yeah, we'll get to that joke later. That's too early. Sorry. 38 protons, so that's part of the nucleus, of course. How much do we need for the rest? 50. All right. So 50 here, right? 50 jimmies. 50 neutrons. Not funny apparently anymore. Strontium. What do we got? 38 and let's say 88, for example. Something like that there would be fine. Okay, and you'll notice that I rounded that number. So if you actually look at strontium there, it's 87.62, so I rounded it up or down accordingly. Don't forget you can round them down. Okay. Good. Questions, anyone? Yes, no? Okay, maybe so. Bad rhymes. All right. So, I guess the important thing to remember with this is, when we talk about, for example, we're going to talk about magnesium here shortly. Magnesium is number 12. It means it has 12 protons, and it's got a weight of 24, and we'll get to that later. But remember, the protons, magnesium has 12 protons. That's what makes magnesium magnesium. If you put an extra well, you can't just put one in, but if you put another proton in there, it's not magnesium. It's number 13 now, so it's aluminum. Okay. The protons are what basically describes each element here. Okay, that's what distinguishes it from another one. So you can't just add protons willy-nilly kind of thing. All right. The next thing I have to tell you about is isotopes, and maybe I jumped ahead a little bit here, but I think I'm going to do this a little differently this class here. Let's just go right down to here. Let's look at this definition here. Do you have to? I think you have all this, correct? Yeah. Isotopes. What is an isotope? Well, isotopes are elements that have the same number of protons. Okay, so they have the same number of protons, but they have a different number of neutrons. And the reason I'm telling you this is because you're going to have a worksheet on this, and it's going to be that's part of it. Okay, so pretty much every element has what we call isotopes. All right, there's different numbers of neutrons in some of these atoms here, and we're going to focus on specifically right now. We're going to focus on some magnesium here. Now, I don't expect you to know this, but there is a few things that I do want you to know. Magnesium. All magnesiums, of course, I just finished telling you this, all magnesiums have 12 protons. That's what makes magnesium magnesium. So that's not going to change. If I'm looking at this one here with the weight of 24, if I wanted to tell you, or if you wanted to tell me how many protons, electrons, neutrons this one has, well, you would say, well, it's got 12 protons, 12 electrons, and in this particular case, 12 neutrons, right? Neutral, so 12 and 12. The weight's 24, so 12 protons, 12 neutrons, 24. There is such thing as this magnesium as well. So it just naturally occurs that way. Okay, it's not that they're all, where you have to do some kind of radioactive thing to it or something like that and jump it or hook up a battery to magnesium or something like that. Just naturally occurs like this. So there is some magnesiums that have 12 protons, because they all do. If it's neutral, it's got to have 12 electrons. That never changes. But obviously the weight's a little bit more on this one. It's 25. So we need to compensate for that by putting an extra neutron in there. And you might say, well, once again, how does that happen? It just happens naturally. All right. And there's even some magnesium that looks like this. Oops. 14 neutrons. Okay. So that's just how they naturally occur. So, by the way, this is the one on your periodic table. So if we actually, and you might say, well, why did we round earlier? What was the point of that? Why didn't we just write down the mass of 24.31? Well, that's fine, you can. The question is, if we do this one, this is 12 protons, 12 electrons, and 12.31 neutrons. Can you have 0.31 neutrons? A third of a neutron? No. You can't have a half of one. You can't have 3/4 of one. No such thing. Coming full, it's a neutron. It's a subatomic particle. You can't have 0.31 neutrons. So you might say, well, why? Where does that 0.31 come from then? Well, it comes from an average of all the possible isotopes you can find. Okay, I'm walking down the street and I'm saying, hey, look, it's magnesium atom right there. That's funny because you can't see atoms. I'll have to explain that to you apparently. And you count up the protons and neutrons and you say, hey, it's got 12 and 12. And then you walk a little further and you say, hey, look, it's another magnesium atom, but this one has 12 and it's got 13 neutrons. And you walk a little bit farther and there's such thing as magnesium with 12 and 14 neutrons. So you're like, well, geez, that just didn't actually happen like that. Well, what's the average of 20? This is not a trick question, okay? If you need a calculator, that's fine. What's the average of 24, 25, and 26? 25 is the correct answer. But that's not the number up there. The problem is, okay, the reason we have these fractions of a decimal here is because they're not all equally. In other words, if I'm walking down the street and I see magnesium 24, there's probably, it's not an equal split. It's not, you know, 33 out of 100, well, 33 and a third are magnesium 24. There's another 33 and a third that are magnesium 25 and 33 and a third magnesium 26. They're not equally distributed. In fact, when you're walking down the street and you say, hey, there's a magnesium atom, there's a good chance, in fact, that's your chance of spotting one of those. Okay? Out of 100, almost 79 of them are that one there. Okay? Magnesium 25, there's about, am I going to mess this up? There's about 11.01. Okay, percent of those. So 11 out of 100 look like that. And roughly, oh, I knew that wasn't right. Sorry. And about 10% look like this here. Now you might say, where did I come up with those numbers? Well, I did a little research in the lab, and I just kind of came up with those numbers. Some dude did that. I don't know who did that. Somebody did. So that's the abundance of each one, roughly. Okay. These are all, here's the important part, these are all called isotopes. So yes, this is the one on the periodic table. Okay. That is an isotope of magnesium. In other words, there's other ones. There's 3 isotopes of magnesium. These are all called magnesium. Okay. All isotopes of one another. That's the important thing. The most common one is the one that has the most abundance of it. Okay? The most common one is the one that you find on your periodic table. Right? Magnesium's 24.31, round that up or down. It's magnesium 24. Magnesium 24 has the best chance of finding that one. There's 79% out of 100 are like that. Is that good? Yes? Did you guys know that? Maybe. Okay. I don't know. Okay. Anyway, that's where that number comes from, 24.31. That's why you get 0.31, and that's why we're rounding it up or down, because it's telling us the most common one. That's not always the one we're looking for either, though. Okay? So the one in your periodic table is the most common. If you look at chlorine, I just happen to know this one as well. Chlorine is 35.45. So the most common type of isotope of chlorine is chlorine 35, rounding it down. There's also chlorine 37. It has a weight of 37. That's another isotope. Okay? Not as common. All right? So, good? Questions, anyone? By the way, I guess we might as well do this right now since I'm bringing this up here. I'm kind of jumping around a little bit, but that's okay. I don't care. It's all there for you. How would I calculate that 24 points? Where do they come up with 24.31? Well, they take into account the abundance of each one. So if you did the math on this, right, if 78.99% looks like 24 and 10% looks like 25, and 11.1% looks like 26. If you do the math on that, do you know what number you get? You could get a calculator and figure that out. You know? What number do you get? 24 point. Yeah, you'd think, but you're wrong, actually. Sorry. That was what I wanted you to say, though. It's actually 24.3202, if I remember correctly. But you might, and then of course, people would say, well, but that's not the number that I wrote down earlier. It's not the same, right? So why isn't it the same? Okay. Well, that's probably something we should talk about a little bit. It's supposed to be 24.31. Maybe the guys on the periodic table messed up. They didn't. Maybe we messed up a little bit. We did. Okay. The thing is what you're going to learn here right away. Just bear with me here. Now this is all in here, and we'll kind of skip around a little bit. The thing is we're assuming a proton and a neutron weigh the same, about 1 each, and that's not entirely true. If a proton weighs about 1, a neutron is a little bit less, has a little bit less weight to it. Okay, it's like 0.98, 0.99, somewhere in there. Okay, so it's about 0.98 to 0.99, somewhere in there. It's a little bit less of a weight to it. Okay, so when we're doing that calculation, we are assuming that the proton and neutron weigh the same. Not quite true. Okay. Now you might say, well, so do we have to redo the calculation and all that stuff? And I'm going to say, no, we don't have to do that. Okay, it's fine. But that's where that number comes from. It's not just 24.31, close enough kind of thing. They've done protons, they've done the weight of the neutron, all that stuff. Electrons, by the way, in comparison, weigh approximately 0. Okay, it's 0.000 something, something, something. They weigh almost nothing. Okay, in the big scheme of things. All right, but that's where that number comes from. So if you do that, that's a good estimation, 24.32. That's pretty good, but 24.31 is the correct number. Okay, a little bit different there. All right, are we good so far? Is that a lot of information to take in or not really? I don't know. All right, well, this just talks about the different types of magnesium, so we've already done that. Okay, so it's fine. The number is what we call the average mass number, so that 24.31 is the average mass. All right. And let's just go back one more here. So this is kind of where we started here. All right. Why did I tell you about the isotope thing? Well, because when you get to this chart here, by the way, let's take a look at your, this is going to be, I'm going to give you some time here. I'm going to quit talking. It'll be nice for a change for you guys. Sodium's 22.99. Make sure you round it up to 23. Okay. Sulfur's 32.07. Make sure you round it down to 32. So make sure you round them accordingly when you're filling this in. Now, they're not all going to be the ones from the periodic table, right? So when you look at, for example, like I said before, chlorine. I know that chlorine is number, what is it, 17, right? Take a look at chlorine on your periodic table just for a sec here. 17, right? It's got a weight of 35.45. But if I told you that this particular chlorine here, let me just actually add a slide in here. Let's say I told you that, for example, chlorine, number 17 here, atomic number, and it's got a mass of 37. Well, guess what? That's not the one from your periodic table, right? Did I misprint it? And the answer is no. That's the one I want you to use. That's an isotope of chlorine. All chlorines have to have 17 protons. So you'd put 17 protons. You got 17 electrons, of course, because it's still neutral. The difference with this chlorine is it's in fact got 20 neutrons here. Most chlorine has 18, 35, right? This one's a little different. So I might give you this number, and I might even give you this number here. And from that, you should be able to figure out, work your way backwards, and figure out that, in fact, well, hey, if it's 17 electrons and it's neutral, it's got to have 17 protons. And if it's got 17 protons, that makes it chlorine. And if it's chlorine, and by the way, this and this, of course, those two linked up will give you that number there, right? So you need to be able to kind of work your way backwards, because the protons and the neutrons always give you the weight. So what I'm trying to say to you is it might not be the one on the periodic table, but it might be an isotope of that. In fact, I think there's 2 questions like that. Okay? So I'll let you guys work on that for a bit here, this thing here, and we'll go over it shortly here. And if you have any questions, let me know. I'll walk around, check on you, make sure everything's good. And if you need anything else, let me know, I guess. All right, so lithium. So lithium has, you're going to find lithium on the periodic table. It's number 3, of course. So 3, okay. That means it's got 3 protons, 3 electrons. The weight here is 7, of course. So if the weight's 7, that all comes from the nucleus, protons, neutrons. So in that nucleus, we have to have, of course, 4, as we like to call them, jimmies. Funny. This one here has got a weight of 16, so it's a little bit trickier, but here it tells you right here, 8 protons. Well, remember that's the same as the atomic number, so 8, that makes it oxygen. Okay. 8 protons, if you've got 8 protons, it's got to have 8 electrons. The weight's 16, so the other 8 neutrons have to make up the rest of that. Iron. It just tells you at the end there, of course. Well, that's Fe here, iron. Geez, I don't remember. This has got to be what, 55.85, right? Is that right? So it's 56, yeah? Okay. So I don't, what is it, 27? Number 27 or no? It's 26, okay. 26 is the atomic number of iron. You'll find that, of course. 26 protons, 26 electrons, and if we got 56 there, the difference, of course, is the number of neutrons. So we'll have the old 30 there. Okay. 52, this one has a weight of, it's also got 24 electrons. If it's going to be neutral, we have to have 24 positives, of course. 24, if you look that up, should be, I believe, chromium. Yeah? Right? No? Yeah, chromium. Please spell these correctly. It's not like I'm asking to like make up words and stuff or sound it out. It's on the periodic table, so you just got to copy it. Okay. 24. Obviously, the rest here we have to get the 52. So that's what carry the 1. 28, I think. Should be there. Hydrogen. Hydrogen's kind of unique. I like hydrogen. Oh yeah. I'll show you. Well, no, we won't. Hydrogen, 1 proton. It's got a weight of 1. Okay, it tells you it's 1.01. So that basically implies that it's got 1 proton, 1 electron, of course, and this one in particular has no neutrons. Okay, that leads itself to some unique properties, which we'll talk about later. We're going to have a pretty chart. We're going to talk about specifically something called hydrogen bonding, about melting and boiling points and how that's related all together and stuff like that. It's going to be fun. The chart is like the like last one of the units, and it ties everything. Oh, it's going to go this way. It's so good. It's so good. It's going to be awesome. Just wait. It's awesome. 13, of course, that's aluminum. What do we need here? This is 27, 26.98. So we're on 27, 13, and 13, 14, of course, is the 27. This one here, phosphorus. Ooh, let's see. Phosphorus is 15, and it's 30.97, yes? So that's what, 31? So we have to have, sorry, that there. 15 protons, 15 electrons, 16 neutrons, yes? Okay. This aluminum, I put this one on here again, and once again, this one's a little bit different. This is not the one from the periodic table, but that doesn't mean anything. How do I know? Well, it's got 13 electrons, 13 protons, 13 atomic number, so it's got to be aluminum. It tells us that right there. This one's got 15 neutrons, so this is one of the other isotopes that is not on the periodic table. In fact, that has a weight of 28. Okay. Number 29, that must be what? Copper? Is that right? Copper. It's got a weight of 63.55. But that might not match up with this one here, for example. So first of all, this is copper. Copper's 29. Actually, well, usually I'd say 64, but I did tell you that there. So I guess right now I put these two numbers in, 29 and 29, 29 protons, 29 electrons. The weight of this one is particularly 63, I guess. So once again, this is the isotope that's not on the periodic table. Okay, it's another option. It's not the most common one, but it is an option. Okay, and good old helium here. Let's see, that's 2. That's got a weight of 4. So we got 2 and 2 and 2, I guess. All right, good. Questions, anyone? Are we good? All right. Okay, one thing that I just want to mention here, you might say, well, you know, I know that argon, for example, it's number, what do we say, 18, right? So we know that argon's got 18 protons. Its mass is 39.95. And you know, you guys have talked about molar mass, yes, and you guys probably know this, but I just want to make sure that you, sometimes we kind of gloss over this, especially in Science 10. 39.95, where does that number come from? How do we get that mass exactly? Well, we average the protons and the neutrons and all that other stuff. Here's what this means, though. Remember, you guys remember molar mass, right? Grams per mole, yes? No? 39.95, and we'd always put a grams per mole here. Well, remember, how much is a mole equal to? It's really big. Yeah. It's, what's Avogadro's number? Yeah. And it could be anything. It could be atoms or molecules or atoms or ions. We'll get to that part. So if you took, all right, this is what this basically is implying here. Really, I've written, these two things mean the same thing, right? I just used the big number instead of 1 mole there. 1 mole is 6.02 times 10 to the 23rd of anything. Or in this case, 6.02 times 10 to the 23rd atom. If I went to the chemistry lab and I got the argon out, okay, and I count, this is going to be your punishment if you don't do homework, right? You're going to count out 6.02 times 10 to the 23rd argon atoms. And when you're done, you're going to call us. We'll go look at the scale. Nothing? Really? I understand it's the end of the day, but seriously, it's a big number is what I'm trying. 6.02 times, if you took that many argon atoms and put them on a scale, counted them up, 1, 2, 3, oh, 6.02 times, the scale would read 39.95 grams. Okay, because it's 39.95 grams per mole. 1 mole is the same as 6.02 times 10 to the 23rd of anything. Okay, if you're not sure about that number, I'll tell you it's 602 like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21. That many. Okay, if you took that many argon atoms, put them on a scale, the scale would read 39.95 grams. Okay. So I'm going to clarify what I said earlier. This is where I get myself into trouble. Don't tell your parents, okay? This is what I was referring to. This number, I had to look it up because I was like, what is that number actually going to be? Like, is it quadrillion? Billion? That's a made-up number. I use that all the time. Cajillion? Also made up. That's not true. I had to look this number up. And then when I looked it up, I was like, no, really, why? Why would it have to be that? How you would say this number is, not lying. Don't forget that part when you talk to your parents tonight, okay? It's 602 sextillion, that's the number of that. Yeah, so, just so you know, that's what I was referring to. 602 sextillion. So, we did not talk about sex today, we talked about sextillion, so don't forget that, okay? When you're talking. That's what that number, that's how you'd say that number. And I thought to myself, well, why wouldn't it? Yeah, of course it has to be. Because why? Email, phone call, right? Alright, so